reservoir management in mature carbonate water flood. Now, when do we call a field mature? A field may be 30 years on production and still not be matured, but another field which may be on production for 10 years but be matured. The maturity of a field depends on the recovery of the field. Surveillance and monitoring. Surveillance and monitoring may sound very similar, but when I talk about surveillance, I talk about inspecting the problem, and monitoring is when you come out with the solution for the problem. So in a nutshell, this is what I'm going to talk about in the next approximate 1 hour. So please stay with me. Okay, so most of you present here might be knowing what water flooding is. Water flooding is when water is injected into the oil or gas formation to do what? To support the reservoir pressure. So when we extract hydrocarbon from a reservoir, we are creating a void in the reservoir which needs to be replenished, and that is done by flooding the reservoir with water. And the second work of water flooding is to sweep or displace oil from the reservoir and drive it towards the production well by creating an oil bank. So by doing these two things, what do we get is increased oil recovery from the existing reservoir. Now, one more thing I just want to share is you might hear two terms, water flooding and water injection. Now, what is the difference? Water flooding is when you are injecting in your producing formation, and water injection is when you are injecting below the oil-water contact. Okay, so now we know what water flooding is. Now let's take a look at the history of water flooding. So a lot of things happen by accident, be it Newton's apple or Archimedes' eureka moment. Water flooding also happened by accident in Pennsylvania in the mid-1800s. So many of the early water floods occurred by leaks from shallow water sands or by surface water accumulations, and they entered the drilled holes. So when they entered the drilled holes, they saw that the wells were having a longer life than permitted by natural depletion. So this way, water flooding gained prominence. Most of you might be reading about drive flooding patterns. So how did the drive come into existence? So in the earlier days, what they used to do is they used to inject from a well. And as soon as the offset producers used to get watered out, they used to convert the offset producers to injectors and thereby forming a circle drive. So this is how the birth of drive injection started. So if you see it, but it was not until the mid-1900s that water flooding gained widespread application. Now, let's see why water flooding is a popular choice. So there are 5 points on the screen. A, water is easily available. B, water is an efficient agent for displacing light or medium gravity oil. A very important point is part C is flooding involves low capital expenditure and operating expenditure and has favorable economics. And water is relatively easy to inject. And finally, water spreads easily through an oil formation. So due to all these 5 points, water flooding is a popular choice of EOR. All right, now you might be a little surprised, what is a cow doing in a slide of water flooding? Well, I tried to create an analogy between managing a dairy farm and managing a reservoir. Now just imagine you are an owner of a dairy farm. So your target is to produce X amount of milk. Now your source is your cow. So the first thing that you would do is to take care of your cow. And what do you need to do? You need to feed the cow at the prescribed time. You cannot just feed the cow any time of the day. You need to have a fixed time. You have to take care of the health of the cow, get vet appointments for the cow. You need to have a team or a person who would take care of the cow too. So after doing all these, you'll be ensured that the cow is producing the X amount of milk that you require. Similarly, when you are in charge of a field or you're managing a field, uh, you are exploiting it. You're taking out the hydrocarbons. So you need to take care of the voidage. So you need to replenish the voidage with water flooding. And the flooding has to be done at the right time, and the right quantity of water needs to be injected. Secondly, you have to take care of your wells. You need to have periodic health checkup of your wells to ensure that the wells are also in their prime condition. And you should need to have a team of people who will take care of all these things, look at all the aspects, and your team should act like a basketball team working together and not like a relay race team who will just pass down the baton to the next person. So, uh, the most important thing when you're managing a water flood is to have a team, do the flooding at the right time, at right quantity of water, and have a surveillance monitoring of your injection and producer wells. Okay, so that was a little bit of the introduction. Now we'll see, how do we choose a field for water flooding? How do we make sure that this particular field is appropriate for water flooding as an EOR? So rather than seeing which fields will benefit from water flooding, let's just see at which fields will not benefit from water flooding. So it is difficult to have an economic water flood if your field is at a water saturation of 50% or more. Now, why? Why is it? Because under high saturation of water, relative permeability has an adverse effect, making it difficult to form an oil bank. So remember in my first slide, I had said the work of water flooding is to create an oil bank, push the oil bank towards the producer well so that the recovery increases. So if flooding cannot form an oil bank, then there is no point in initiating flooding in that field. Water flooding is not effective in thick reservoirs with horizontal and vertical permeability. Why? So if you have high permeable streaks, now what will happen? Your water will rush through those high perm streaks. The high perm streaks will behave like a conduit, and you are flooding your reservoir so that pressure is maintained, but instead all the water that you're injecting will move through the streak and get produced through your producer, which you do not want. So it's better to avoid flooding in these kind of reservoirs. If your injectors and producers are located along a line parallel to the fracture direction, then also it will be a problem for you, because here the fracture will be acting as a conduit. So better to avoid flooding in that scenario. And lastly, in highly heterogeneous reservoirs, if there is no clear communication between your injector and producer, then you might not know where your water is going. Your water might not reach your producer, might not be able to create the oil bank. So it is recommended to avoid flooding in highly heterogeneous reservoirs. So now that we know where not to flood, let's see what is when is the right time to start water flooding. Water flooding results in maximum oil recovery where reservoir pressure level is at its original bubble point. Why is it so? Because at that pressure, reservoir oil viscosity is at minimum value, which improves mobility and aerial sweep. The producing wells at that time are at their highest PI, and there's no delay in flood response as reservoir has no free gas at that point of time. But reservoir with high formation volume factor and high solution gas oil ratio, they should be flooded slightly above the bubble point pressure, because it is seen that in that kind of reservoirs, the viscosity is minimum at that pressure. So now there's a common argument that optimum pressure is slightly below the bubble point pressure and not at the bubble point pressure, because presence of gas saturation reduces residual oil saturation to water flood. Theoretically, yes, but practically it is very difficult to achieve throughout the field, and a large variation of gas may affect the flood negatively. So in actual practice, you may not be able to maintain that pressure throughout the field, And in some places, you may have more gas that has escaped, and that will again affect the flooding response negatively. Okay, now I come to the second part of my presentation, that is water flood surveillance and monitoring. Okay, so when you're in charge of a reservoir on water flood, you need to keep in mind these three words, or I keep in mind these three words: operate, monitor, and evaluate. So how do you do this? We have to monitor the reservoir, the wells, and also the surface facilities. As I said, we need not see just one parameter while monitoring. We have to see the whole picture. We have to evaluate performances against given matrices. So you plot some kind of curves for your field and then compare it with the given matrices to see whether your field is behaving properly, whether your wells are behaving properly or not. Modify reservoir model as additional data are obtained. So you should be open to generating new data and then modifying your existing plan based on the new data generated. So it has to be a dynamic process. It cannot be just a one-time thing. You have planned it and this is how it goes. No, water flooding is highly dynamic and it should be updated with the amount of data, with the new data that you're generating. Identifying new opportunities for expansion. Well, we as humans, suppose at age 20, your reflexes are good, but when you turn 60, your reflexes become poor. Similarly, a water injector well in its prime, the amount of water it injects will not be the same after 10 or 15 years. So that's why we need to identify new opportunities for expansion, because in a water flood, the amount of water to be injected will increase with time. So you need to have a plan to convert more wells into injectors, or rather expand your flooding. And as every good thing should come to an end, a reservoir engineer should plan an exit strategy for terminating the water flood, because water flooding should be done up to an economic limit. After the economic limit, continuing water flooding will not bear you any results. Okay, now there are a couple of questions on your screen. So what I am going to do now is to answer each and every question. We'll look at surveillance first at field level and then the well level surveillance. So let's move on to the next slide. Okay, so it's a very interesting slide. The couple of bright colored plots on your screen. So let's look at the left-hand side plot. In the left-hand side plot, we have plotted reservoir pressure, current reservoir pressure to its original pressure in the y-axis, and the recovery efficiency, that is amount of hydrocarbon recovered to its original oil in place or gas in place. This is oil in place. And you see some colorful plots here. I'll just explain one at a time. So this blue one is the plot for a reservoir which is producing with liquid and rock expansion drive. This brown one is on solution gas drive. This green one is on gas cap expansion. The purple one is on water influx, and this cyan one is on gravity drainage, which is again a more ideal type of reservoir, which we don't see that commonly. This blue line with orange dots is the data of a real field. So what happened here? The field was put on production. Now we see that the plot resembles a reservoir on solution gas drive. But then an event occurs in the life of the field. The field is put on water flooding. And that's when we see the plot changes and it starts resembling a field on water influx. All right. And then the second event happens in the life of the field. That is there was a drop in injection rate in that field for certain reason. And then we see the plot dipping again, or rather resembling the solution gas drive mechanism. Now, if we see other parameters of the same field with the same event, so this is where I've plotted GOR. So initially the field is producing on solution gas drive mechanism. So the GOR shoots up, but as soon as the field is put on water flooding, the GOR drops and is stabilized. But when the second event occurs, that is water injection rate drops, the GOR again starts picking up, which shows that the field is again producing from solution gas drive mechanism. The liquid performance of the field, if you see, before starting of injection or flooding, it is low, and then it shoots up as soon as the field is put on flooding, and then it's maintained. In fact, it increases. But after the second event, the liquid production of the field falls. By liquid, I mean to say oil and water together. So these plots again denote that the field is very much dependent on water flooding, and it benefits also from water flooding. So now let's look at the second question. What is the current recovery factor and how much pore volume of water is injected in the field? So these are the kind of plots that you should be plotting for your field if you are, or rather you can plot for your field if you are doing a water flood surveillance. Before moving on to the plots, I'll just explain hydrocarbon pore volume. Most of you here might be knowing the oil initially in place formula, where it is hydrocarbon pore volume to the oil formation volume factor, where hydrocarbon pore volume is the product of area, thickness of your reservoir, porosity of your reservoir, and saturation. And pore volume injected is the volume of water injected to the hydrocarbon pore volume. Now, let's concentrate on the left-hand plot. Here, the recovery factor is in the y-axis and the pore volume injected is in the x-axis. Let's look at the plot of the first field. So we see before starting of water injection, the recovery of this field is very low. And with injection or with more pore volume injected, the recovery increases remarkably. But the more interesting part are these two fields. Here, the recovery is already above 20% for both these fields before starting of injection. But for Marco field, we see that the recovery factor increases very gradually with increased amount of pore volume injected. But for the Marin field, the plot is going nearly vertical, which shows that the field has immense opportunity to increase its recovery with more pore volume injected. So what I did was I plotted a similar plot for one of the fields that I'm working with. And I saw that the initial recovery before the field was put on water flood was around 5%. But when water flooding started, when the pore volume injected increased, the plot was going vertically, which showed that there was immense capacity for the field to increase its recovery with water flooding. So these kind of plots are very indicative, and this will help you in deciding whether you should go on with water flooding or you should stop. Okay, so a little more on pore volume water injected. So it's an industry practice to assume that a water flooded field will reach its economic limit when 1.5 to 2 pore volume of water is injected. And assuming a value of 2 pvi in the life of the field, and assuming the life of a water flood is around 20 years, average injection of around 0.1 pore volume per year should be obtained in the field. So the recommended range of pore volume injected is 0.05 to 0.2. So if you see that the field that you're working with is injecting less than 0.05 or more than 0.2, then we should stop and see why isn't it in that range, and then come up with remedial measures to bring it to the prescribed range. Okay, another interesting plot, and I need all your attention for this. How is the static reservoir pressure behaving with time? Now let's look at this plot. You see green dots and blue dots. Let me break it down for you all. Green dots are the pressure recorded in the oil producers, and blue dots are the pressure recorded in the water injectors. Now, how to get the static pressure? For a producer, you close the well, you let the pressure build up, and after a point, it might be 24 hours, 48 hours, 72 hours, the pressure will stabilize. That is the static pressure of your reservoir. Similarly, for injectors, a flowing injector will be placed at a higher pressure than your static pressure of the reservoir. But when you close the flowing injector, the pressure in that well will start falling. And after a point of time, again 24, 48, or 72, it will stabilize. And that is how you'll get the static reservoir pressure from your injector well. Now let's look at this plot. So in this field, if you see the pressure recorded in the producer wells, the pressure trend shows a drop in pressure till water flooding started in the field. And once water flooding started, the pressure in the producer well starts increasing. Another thing you should notice is the green dots and the blue dots are very close to each other, which should actually be, because if your water flooding is uniform, then the pressure recorded in your water injector and the pressure recorded in your producer should ideally be the same. But what problems happen with the field? Let's see. With time, the pressure started falling, and the blue dots and the green dots, now there is more gap between them. So why this happens is because with time, the dissipation around your injector reduces. Skin forms in your injector well, and then the water cannot move towards the producer. So all these problems, these might be the problems for this kind of a plot. And as a manager of a water flood, this is our work to see, identify these problems and take a remedial action to solve the problem. This is another kind of plot which you can plot with pressure. And so the pressure depletion is in the y-axis, and the CVC, or the cumulated voidage compensated, is in the x-axis. By pressure depletion, I mean, again, current pressure to original pressure. So ideally, the graph should be flat. But here we see some problem happening in this here, because the graph is going vertical. So the pressure is depleting in the field, but the cumulative voidage compensated is not increasing. So this, if you plot a similar graph for your field and you see this is what is happening, then definitely you should be alerted, and you should definitely intervene and find a solution for this problem. Okay, I just spoke about cumulative voidage compensated. Now let me just explain it a little bit for you all. I'm sure most of you here have seen this equation. So on the left-hand side is the total cumulative production, and it is getting balanced by total expansion, aquifer influx, water injection, gas injection. This is your typical material balance equation. But what if the total expansion is negligible? There is no active aquifer in the field. There's no gas injection. So the total cumulative production has to be balanced with the water injection. Then what happens? So this is a plot where the yellow portion is the voidage created. By voidage created, I mean this. That is the oil that is being extracted, the gas that is being produced, the water that is being produced. Now, if you have only water injection to compensate it, you have to inject water of that amount, which will cover the yellow part, or else the amount that you're extracting from the field, that much amount or more than that should be put into the reservoir. So ideally for this kind of a reservoir, which doesn't have any aquifer influx or a gas cap, then you're totally dependent on water flooding, and the volume of water that should be injected in this kind of reservoir should be between 100 to 120%. So we have terms like VRR, or voidage replacement ratio. So if you see your yellow part is being covered by your blue part, that means your voidage replacement ratio will reach 100% or more. But if you can see a little bit of yellow, that means your voidage replacement ratio is dropping. It is below that 100 mark. And that's when you again need to intervene and increase your injection. Okay, so I spoke a lot now on what should be done and what shouldn't be done. Now, how a good water flood should look like. So this is a plot showing how the parameters will look like in a good water flood. Obviously, water production rate will increase. Without any doubt, the amount of water production will increase with time if your field is on water flood. But along with that, what you'll see is the oil production rate will increase and then get stabilized. And the GOR will decrease and get stabilized. The water injection rate needs to be upward. It should not fall down, because as I had shown in one of my initial slides, if your water injection rate is falling down, then it will again impact the total amount of liquid that you're producing from your field. And the reservoir voidage should be maintained. So you can go back, if you have data of your field, if you're working with a field, you can plot this and see if it resembles something like this, then your water flood is working fine. You need not do anything. But if it does not resemble, then you should definitely intervene and come up with some remedial measure. Okay, another interesting plot. This is a WOR versus cumulative oil plot. So water oil ratio is plotted in the y-axis and the cumulative oil produced in the x-axis. Now the plot it will have an increasing slope, but it will be gradual. But if you see that the plot is going vertical, that means the water that is being produced in your field is much more than that should be produced. That means that there is a lot of water that should be in the reservoir is coming out through the producer, which is not good. And you should definitely go back and check the reason for that. You don't want the water to come out of your field too early. And what you can do is you can set an economic limit. So here I have set an economic limit of 95% water cut. That means if my producers reach 95% water cut, then I'll stop those wells from production. I'll not flow those wells anymore, because that is no more economic to me. So by plotting this curve, we can monitor the trend, and flatter curve will lead to more recovery, and water flood to be evaluated if the curve shows steep rise that I just explained. Another interesting plot, and I really found this plot very useful while working, so I just wanted to share with you all. For this plot, first we have to divide our plot in 4 quadrants. And what are we plotting? We are plotting oil ratio and water ratio. So this plot can be for a small sector of your field. It can be for a particular layer. It can be for a particular group of wells. It depends on you. I have taken a time period of 6 months. And why? Because for me, shorter period did not show any significant change, and longer period created difficulties when trying to identify the root cause. So what did I plot here? So I took oil rate of June and compared it with January, oil rate of July and compared it with February. So I had the 6 month gap. Similarly, I also compared the water rate. So these are wells. Now, if your wells or these points are lying in the top right quadrant, then what is happening? That means your wells are responding to flooding. The total liquid is increasing in your field. So you need not do anything. So what you have done is great, and just continue what you're doing. But if you have points in the bottom right quadrant, so then it indicates that there is more water production in your well. So if one or two wells or points are there, it's all right. But if most of your wells are falling in this area, that means something's not going right with your water flood. You're producing way too much water than you should produce. Maybe there are some streaks. Maybe you've placed your producer injector across a fault, along a fault. So these give an indication that whether your flood is behaving properly as it should or not. And then these give you an idea, and then you can take a decision based on that. Come back to the plot again. If your points are lying in the bottom left-hand corner, that means your liquid rate, your oil production, your water production, both are decreasing. So this is not what you want. But again, at the same time, if you just have 1 or 2 points here, then you need to find out, is there something wrong with your water flood, or is there something wrong with that particular well? Because a dropping liquid can even be due to a faulty gas lift. So as I said, your water flood team should behave like a basketball team. You should not just look at one parameter, but see other parameters too, and then come to a decision and find out the root cause of your problem. And if you have some points or wells falling in this quadrant, top left-hand side quadrant, that means the water production was initially more in January, but it has decreased in June. That is because if there are some points in this plot, in this quadrant, the wells mostly are new wells, because initially new wells, the water production might be more because of the completion fluid that flows back, but with time that water production rate decreases. So this is again a very good plot for surveillance of your field on water flood. Now let me go to some well-wise plots. So till now I was discussing field level surveillance. Now I've come to well level surveillance. So this is something, this plot is known as chance plot. On the left-hand side, or in the y-axis, I'm plotting water-oil ratio or its derivative. And in the x-axis is the time in days. If your WOR plot is shooting up, as a positive slope shooting up, that means it's a case of channeling. So the reason for water production in a well is due to channeling. But if your WOR plot does not show a quick shoot up, but it is gradual, and then it becomes flat, then it is a case of bottom water coning. Now, if we take a look at the WOR derivative plots, it is similar for channeling as WOR plot, but in case of coning, the WOR derivative plot has a negative slope, so it falls down. How this is helpful. So I went ahead and plotted it for some wells in the field that I'm working with. And this is for one well. If you see that the WOR plot is flat here, and the WOR derivative is kind of having a negative slope. So it denoted from this plot that it is a case of bottom water coning. And we did go back and we looked into the well, and we did find out, yes, it was a case of coning. So this plot gave us a lead to at least think that it may not be just channeling, it may be a case of coning. Whereas in this plot, we had plotted WR and WR derivative, both are shooting up, and we went back and we found out that yes, one of the injectors close to this producer was responsible, and then we went back, fixed the injector, we did a profile modification job in that injector and made sure that the water is going in the right direction. So we had seen a well-level plot for a producer. Now it is a well-level plot for an injector, which is a Hall's plot. Hall's plot is when we are plotting the cumulative pressure in the y-axis and the cumulative water injected in the x-axis. Ideally, your injector should, the plot should be a 45-degree, but if your plot is going vertical, then what is happening? Your cumulative pressure, when I talk about cumulative pressure, I'm talking about injection pressure in your injector well, is increasing, but your cumulative water injection, the amount of water that you're injecting in the well, is not increasing. That means there is a barrier that the water is facing. So it might be a case of positive skin in your well, because over the time, continued injection leads to formation of scales in your injector wells, and it needs to be treated with acid from time to time to clear the scale, stimulate the formation, it will reduce the skid, it will go negative, and then your injection will go in the direction that you have planned it to be. Again, if your plot is horizontal, so what is happening? Your cumulative pressure is not increasing, but more and more amount of water is going into your reservoir. This is a serious case. That means it can be a case of injection at fracture pressure or higher than fracture pressure. So if you're injecting in a reservoir at or above fracture pressure, you're inducing fractures in the reservoir, and these fractures, they'll act as conduits, and your amount of water that you're injecting will start to get produced through your producers. There'll be a case of early water breakthrough, and even serious cases if you're having out of zone injection. Out of zone injection will lead to water moving to places where you don't want, and this may cause much more serious issue like subsidence of a platform. So if you see your plot is going horizontal, then definitely it's a red alert, and you should stop injection and see why it is going that way and rectify the problem. Okay, so I've explained many plots. Now let's see what are the global standards of water injection. What are the practices, international practices? Start early water injection and then maintain voidage replacement ratio between 95% to 120%. VRR of 1.2 is recommended for peripheral water floods, but for pattern water floods, it is recommended to be below 1. Why? Because when you're injecting, you only have a peripheral line drive, so you're injecting from away from the producers. But when you have a pattern flood, your producers are part of the pattern, so you do not want to water out the producer. You want to ensure that your voidage is getting replenished, you're injecting enough to maintain the pressure. So it is okay if you maintain VRR at 1 or just below 1. Another very interesting point that I have implemented in the field that I'm working with, and I found success, it actually helped me, was by applying unsteady water flooding condition. So what do we do here is we inject for 6 months and then we stop injection, and then we or maybe we inject for 6 months at some particular rate and then we reduce the injection. So this cyclic injection, what happens is we have found out that the ultimate recovery improves in the wells, in the producer wells, because by controlling the water produced, we are producing more oil, and thereby the recovery also increases in this case. There is no theoretical proof, but it is something that is recommended. People are doing it in the industry across the globe, and it really helps rather than having a continued water flood 365 days. The cycling water injection is beneficial. Just a couple of slides on the surface facility of water injection. I'm working with an offshore field, and this is how the setup looks. Seawater is pumped in, it goes through coarse filter, fine filter, then goes to a deoxygenated tower, and then to a booster pump, then it goes through the main injection pump. And in between, we add corrosion inhibitors, bactericide to make the water more appropriate for your reservoir. And then finally, it goes to the wellhead platform. So water needs to be treated so that it is suitable to be injected in your reservoir. So the quality of injected water is as important as the quantity of injected water. We have, in my presentation till now, I've spoken about how much amount of water should be injected, but very important is what you are injecting, the quality of the water. So these are the parameters, or these are some of the additives that we are adding to the water to maintain the quality, and this is desired value of the injected water. So if the quality of your water is within this limit, then it's all right. You're injecting good quality water, you need not worry. But if it is below or above this, definitely you should change the quality of water that you're injecting, because a poor quality water will hamper not only your wells, but also your reservoir adversely. Okay, so we were using flip phones nearly 15 years back, and now we have moved on to smartphones. Now, why shouldn't it be the case for water flooding too? So now we have the concept of smart water flooding, or low salinity water flood. So what happens here is we are tailor making the water for your reservoir. So the salinity of the water that you're injecting is being changed and made suitable for your specific reservoir. And how are we doing it? We are doing core flood experiments. We are injecting, in the experiments, we are injecting at different salinity and finding out what is the optimum salinity at which we are getting maximum recovery from the core. And then we are trying to implement it in the field. So what happens? So how does low salinity water helps in enhanced recovery? Let's take a look. Okay. It is believed that microdispersions are formed in the oil phase when low salinity water comes in contact with crude oil. Microdispersions deplete the surface active components at the oil brine interface, and this changes the balance of forces at the rock brine and oil brine interfaces and results in wettability alteration. It might sound a little tricky, so let me explain it with the diagram here. So these yellow charged particles are the hydrocarbon or the oil particles. So what happens is when we are injecting low salinity water, the sulfate ions, they push the negatively charged oil ion, and it takes its place. So basically they are reversing the wettability of the formation. So from oil wet, here it becomes water wet, and the oil is pushed out of the carbonate, and it gets produced. Okay, so things to remember before I end my presentation. Key ingredient of surveillance program is planning and accurate data collection. To understand reservoir flows and reduce non-uniqueness in interpretation, it is crucial to implement a multi-level surveillance effort. As I said, only one parameter or monitoring a single parameter will not give you results. You need to look at the whole picture, look at different parameters and base your decision upon it. And single technique in isolation is not generally indicative, as I said, because different parameters can cause similar plot signatures, how I had explained it in that ABC plot, where drop in liquid level can denote, not only denotes that there's something wrong with your water flood, but maybe there's something wrong with your lifting in the well. And surveillance techniques should always be precursor to in-depth studies, including simulation. So these surveillance techniques, these are very indicative, but it helps a reservoir engineer to monitor the field, to monitor your wells, monitor your reservoir, and this will give you the scope to do something more, to plan something more, either by simulation, it can be to find out the channels that you might be creating with water flooding, continued water flooding, or any other kind of in-depth studies. Okay, so I benefit